Problem 82. Use calculus techniques to graph the function x cubed minus 3x squared minus 9x plus 27. First, we're going to look at the original function. We're going to use the function itself and find the intercepts. To get the x-intercept, we would set y equal to 0. So we have 0 equals x cubed minus 3x squared minus 9x plus 27. And it's not obvious how to factor this, so we'll save this step until later. We'll come back and look at the x-intercepts at the end. For the y-intercept, we'll set x equal to 0, and this gives us y equals 27. This gives us our first important point, is that we plugged in x equals 0, got y equals 27. Next thing we'll look at is the first derivative. The first derivative gives us critical numbers, intervals of increase and decrease, and extrema. So take the derivative of the function. We've got that f prime of x is 3x squared minus 6x minus 9. And I see that this is defined everywhere because it's a polynomial. However, we need to set it equal to 0 to find our critical numbers. So we'll set this equal to 0. And I see that everything here is divisible by 3. So dividing by 3 gives us the equation x squared minus 2x minus 3 equals 0. And this we can now factor as x minus 3 times x plus 1 equals 0. Splitting this into two equations, we get x equals 3 and x equals negative 1 as our two critical numbers. Now to set up our intervals of increase and decrease, we've got x equals 3, x equals negative 1. Let's pick some test points in each one of these intervals. So to the left, I'm going to pick x equals negative 2. Between the two of these, x equals 0. And over to the right, say x equals 4. Our derivative then, if we plug negative 2 into the derivative, we get positive 15, which tells us that the function is increasing. We plug in x equals 0 into the derivative, and we get that the derivative is negative 9. Since the derivative is negative, we know the function is decreasing. And then over on this third interval, if we plug in x equals positive 4, we get that our derivative is positive 15. And again, being positive tells us the function is increasing. So we can see from this very rudimentary graph that x equals negative 1 is a maximum. So if we plug this back into the original function, we get positive 32. So our maximum is negative 132. And our minimum occurs at x equals 3. If we plug 3 into the original function, we get 0. Okay, so now we have three important points. We have the y-intercept, we have the maximum, the minimum. Now let's move on to the second derivative. So the second derivative is all about concavity and inflection points. So our second derivative, going off the derivative of f prime, we've got 6x minus 6. Again, this is defined for all values of x. So to find our inflection points, we're going to set this equal to 0. We can divide both sides of this equation by 6, and we've got x minus 1 equals 0. So this says x equals 1 is our only possible inflection point. So what we'll do from here is set up another interval. X equals 1 is the only critical number, so to speak, on here. So we'll choose some xi's on either side. I'll take x equals 0 and x equals 2. So our derivative, if we plug x equals 0 in here, we get that our second derivative is negative 6. If we plug x equals 2, we get that the second derivative is positive 6. So if the second derivative is negative, that tells us the function is concave down in this interval. Over here, our second derivative is positive, so we know the function is concave up over in this interval. And since it changes concavity at x equals 1, we know that this is an inflection point. So we have a point of inflection at x equals 1, and if the x value is 1, our y value is 16. So now we have enough information to make a sketch of this function. So we know that if we look at our 4 points that matter so far. Our first one is 0, 27. So up here at 0, 27, we have our intercept. We have a maximum over here at negative 132. Negative 132. So the function maxes out here, passes through the intercept. Over at x equals positive 1, it changes from concave down to concave up. We have our minimum at x equals 3, y equals 0. So over here we've got our minimum at 3, 0. So it comes in, minimums out here, and then increases over to the right. And then on the left-hand side, it continues on over on this side, but we want to know where this other intercept is. So we can finally figure out what this last point is by going back to the original function. Remember, we had skipped this in the beginning. To find the x-intercept, we needed to solve this equation right here. Now, we already know that x equals 3 is one solution to this. So what we can use is synthetic division. We can take our polynomial. Let me write this in black. We can take our polynomial, x cubed minus 3x squared minus 9x plus 27. And we can use synthetic division with x equals 3. So we'll bring this 1 down, multiply by 3, we've got positive 3. Add these together, we have 0. 3 times 0 is 0. Negative 9 plus 0 is negative 9. 3 times negative 9 is negative 27. We add these together, we get 0. Now remember, this 0 is our remainder. So this part right here looks like x squared minus 9. So what we've done is we've factored out x minus 3. So we've taken the original function, we've factored out the x minus 3, and what's left over, our quotient then is x squared minus 9. And we can factor this up further. This is a difference of squares. We can factor this as x minus 3 times x plus 3. So x equals 3 was our first intercept. X equals negative 3 will be the second intercept. So over here at negative 3, 0 is the other x-intercept. Now we have our complete graph. We've got our intercepts, our max, our min, our point of inflection, and that's our graph.